Glasgow, the Govan area beside the Clyde shipyards. Much of this area's run down. It's been hit badly by the recession. But like anywhere else, the people here in Govan need doctors and health care. And it's in this health centre that a new piece of equipment is helping the doctors with their work.
That's fine. Now, Catherine, if you'd like just to sit down. This is the machine that I was explaining to you about earlier on, and what I want you to do is just to answer the questions as they come up on the screen.
This small computer has been programmed to investigate dyspepsia,
I won't be
stomach
using the mic
illness.
while you're answering the questions. I'll leave the room at the moment. If you'd like just to let me know when you're finished. Thank you.
It asks a series of questions about the symptoms, their nature, degree and frequency. The questions try to distinguish between different causes of dyspepsia. The patient answers using a specially designed keyboard, and after each answer, the computer works out probabilities for the different possible diseases. The computer was installed after preparatory work carried out at one of the major hospitals in Glasgow. One of the specialists there, Dr. Robin Nill-Jones.
Well, we think this is an important system because dyspepsia, which is the subject we've been interested in, is a very common condition. It accounts for somewhere up to 20% of all general practitioner consultations. It accounts for probably 6 to 8 million days off work in the country as a whole. And in this condition, there are many possible diagnoses, some of which should certainly be seen in hospital, but many of which should be managed at home. And the object of this research is to try to sort out patients into those who are much better managed by their own general practitioner and those who actually need to be seen in hospital by a consultant or by appropriate investigators. Now, it happens that in dyspepsia, the history is the single most important part of what the patient can tell you. You can obviously examine him and find certain things, but the history itself is almost paramount. And so here we are in this situation with a common condition, with a history being very important, wishing to perhaps better distribute the way patients are managed between general practitioners and hospitals. And we find, of course, that we can automate the history taking, and our 10 years of work in this field have shown that patients really quite like being asked about their history by a computer, which it does reliably, and it doesn't get tired, and it certainly doesn't get cross, and the telephone, of course, does not disturb it. So these things are all pluses towards the computer taking histories, and patients quite like it. Now, of course, they understand that the decisions will still be made by the doctor that they're seeing, but nonetheless, they're prepared to give the time to the computer so that an accurate and highly reproducible history can be taken.
From the patient's history, the computer identifies likely diseases for the doctor. Duodenal ulcer disease, or perhaps irritable bowel syndrome. And as well as suggesting treatment, it also gives the probabilities of each disease. The odds are 7 to 1 on duodenal ulcer. And now the doctor can decide whether the patient must see a specialist or whether he can treat the disease himself. And that's an important use of probability theory, assessing the probability that a patient has a particular illness. The computer asks a series of questions and consequently calculates some probabilities. This is a record of part of that computer consultation. It wouldn't normally be printed out in this form, but we've arranged it to show you that each disease has a probability, and that as each question is answered, these probabilities change to reflect the answer given. The questions are designed to discriminate between diseases, so that most of the time, just a single illness finishes up with a high probability, and the remainder will have much lower probabilities. In the Glasgow experiment, there are dozens of questions which could be asked, and so some quite complicated probability theory is needed. But to give you an idea of the type of reasoning that's involved in the calculations, we'll look at a more restricted problem. We'll also introduce a concept which is vital to the understanding of problems of this kind, the concept of conditional probability.
Let's start with a restricted problem. What we've done is to limit ourselves to 3 major illnesses, which all give rise to stomach pain. That's a duodenal ulcer, an ulcer in the small intestine, a gastric ulcer, an ulcer in the stomach, and a rather more serious disease, gastric cancer. We've represented the 3 illnesses on a Venn diagram. The whole diagram stands for the universal set. It's meant to represent the people in a particular area, like Govan in Glasgow, who've gone to the doctor with stomach pain. And since, at this stage, we want to keep the analysis simple, we'll assume that these complaints are exhaustive and exclusive. Exhaustive means that someone with stomach pain must have one of these complaints. There are no other possibilities. And exclusive means that if a patient has one complaint, then he can't have any of the others. You can only have one of these 3 illnesses. So those are our assumptions. How can we assign probabilities? We'll start by using some symbolism. We'll call the 3 diseases D1, D2, and D3. Now, can we assess the initial probability that the patient has one of these diseases before the diagnosis starts? In this part of Glasgow, over the past few years, there have been 269 instances of duodenal ulcer, 54 instances of gastric ulcer, and 22 instances of gastric cancer. So that's 345 cases altogether. And we can plot the relative frequencies of the 3 illnesses alongside. We'll use these as the initial probabilities, before we've questioned the patient. But how do we arrive at the modified probabilities after the first question's been answered? One of the questions the patient has to answer is, does the pain occur daily? This patient's answer is yes, and that affects the probabilities. We started with this large event space, the space of all the people in Glasgow who've suffered from one of the 3 diseases over the past few years. But only some of these people have had a daily pain. So if we restrict our attention to just those people, the relative frequencies of the people suffering from the 3 diseases will be considerably different. If we know the pain occurs daily, the probability of gastric cancer turns out to be considerably higher. We give a name to this type of probability. It's called conditional probability. Conditional because we know some conditions involving the event in question, which means that instead of having the whole event space available, we're restricted to a subset of it. And we use this symbolic notation for conditional probability. If the event we know is the symptom S, in this case that the pain occurs daily, then we write the probability of D1 given S, the probability of a particular illness given that we know the symptom has been observed. And in practice, it's these conditional probabilities, based on lots of symptoms, that are used to build up the final diagnosis of the illness.
So the language of conditional probability is used to tell us how the probabilities alter as the patient answers more and more questions. What happens is that as each question is answered, the conditioning event S is different as more and more symptoms are recorded. For instance, at a certain stage of the questioning, the conditioning event might be that the pain occurred daily, and there was no vomiting, and that the patient's age was over 60, and so on. Eventually, we want to arrive at a conditional probability that a patient suffers from a particular disease, given that a number of symptoms is recorded. Well, that's what we want, but the data isn't quite in that form. Dr. Neil Jones from Glasgow.
Well, the probabilities came from a lot of work done by a number of consultants who in fact interviewed the patients themselves, and we've now seen about 1,500 patients in this way. This work started before we had the computer to do the full interview for us, of course. Now, in order to do this, we had to agree on definitions of symptoms. For example, here we have the definition of nocturnal pain, which is that patients wake up in the night with their pain, and in order to get relief, they have to take milk or a snack or something like antacids. When we had then analysed the patients, we had 900 patients when we did our first major analysis, and this gave us some conditional probabilities of symptom-given disease. For example, if we stay with nocturnal pain, this is well known by physicians to be associated with patients who have duodenal ulcers. And we find that patients with duodenal ulcer, about 40% or so, wake up at night and get relief from their pain by one of these manoeuvres. It's quite often found in patients with gastric ulcer and even gastric cancer. But in patients with, for example, colonic disease or some other different cause of their dyspepsia, waking up at night and getting relief by antacids is quite rare. It occurs in only 9 or 10% of them. This is therefore a highly discriminating indicant, particularly helpful for the diagnosis of peptic ulceration. There are, of course, other examples, and here is one from age. And so we find here that only 9% of our patients with duodenal ulcer were over 60, whereas of our patients with gastric cancer, more than 2/3 were over 60 years old.
So the data from Glasgow is pretty comprehensive. It covers all the different symptoms which the computerized diagnosis system is designed to examine. But as we've seen, the conditional probabilities are the wrong way around. They tell us what the probability is that a patient will exhibit a certain symptom given that he's got a particular disease. That's not, in practice, what we want to know. We want to find out the probability that he's got a particular disease given that he's got a certain symptom. So we can't use this data directly. Somehow it has to be processed. The way we process it is to use Bayes' theorem.
What is Bayes' theorem? It's simply a way to interchange the two events in the expression for conditional probability. We're told the probability of S given di, the probability of the symptom given a disease. What we want is the probability of di given S, the probability of a disease given the symptom. We can calculate it using this formula. We'll use Bayes' theorem to find the probability of D1 given S. That is, the restricted event space is S, daily pain. And we want to find the proportion of patients within that space who have the disease D1. So that's what we want. Bayes' theorem says we can work it out in terms of 3 other quantities. The first one is the conditional probability the other way around. That's the probability of S given D1, the probability of a daily pain given a duodenal ulcer, data which the doctor provided. That's multiplied by the probability of D1, the initial probability of a duodenal ulcer, which we used earlier. So now there's one item left, the probability of S. That's not given to us directly, but we can work it out. There's a formula we use to calculate this term, P of S, in the denominator, using the known values of the numerator. It's called the theorem of total probability. And all it says is that we get P of S by summing the values of the numerator over all possible conditioning events. In our case, we had 3 such conditioning events. Let's see how it comes about by looking at the Venn diagram. You can express the event S in terms of its intersection with the 3 diseases D1, D2, and D3. These 3 intersections are mutually exclusive. So the total probability of the event is the sum of the 3 probabilities of the intersections. And we can write these in terms of conditional probability. Take the probability of S intersection D1. In terms of the diagram, it's the number of people in the shaded region divided by the total number of people. Represented as a fraction, we can write it as the product of two fractions. It's the shaded region as a proportion of the D1 region times the D1 region as a proportion of the whole region. So that's the conditional probability of S given D1 times the probability of D1. The same goes for the probability of the other intersections. And since the probability of S is the sum of the probabilities of the intersections, we can rewrite it in this form, using conditional probabilities. Finally, we can use a sigma to represent the sum. So that's an expression for P of S in terms of probabilities that we know. And that's the final quantity needed to use Bayes' theorem. Here's the data we're going to use. These are the initial probabilities of the three diseases. Duodenal ulcer is most likely, followed by gastric ulcer, and then gastric cancer. And these are the conditional probabilities of having a daily pain given the three diseases. They're the probabilities provided by the doctor. Now, what happens to the probabilities once we know there's a daily pain? With a duodenal ulcer, a daily pain is rare. So we'd expect the probability of that, which starts high, to go down. On the other hand, a daily pain is quite common with gastric cancer, so we'd expect the probability of that, which starts low, to go up. But what about a gastric ulcer? The chance of a daily pain is comparatively low, but it's quite possible. So would you expect the probability of a gastric ulcer to go up or down? It's difficult to tell intuitively, so let's use Bayes' theorem to find out. We'll calculate the probabilities using our computer. I'll enter the initial probabilities of the three diseases. First, the duodenal ulcer. That's 0.780. Then the gastric ulcer, 0.156. And finally, the gastric cancer, 0.064. But we know that the patient suffers from daily pain. So I'll enter the conditional probabilities of a daily pain. 0.089, 0.267, and 0.667. And now these are the new conditional probabilities of the three diseases. Let's compare them. First, the initial probabilities. And this is how they've changed. The probability of a duodenal ulcer, that's on the left of your screen, has gone down, as we've expected, although it's still quite high because it's a comparatively common ailment. On the right, you can see the probability of gastric cancer has gone up considerably, because a daily pain is a common symptom of that disease. But what about a gastric ulcer, the one in the middle? The probability of that has gone up too, from 0.156 to 0.271, even though only a quarter of the gastric ulcer patients get a daily pain. And that's perhaps counterintuitive. We might have guessed the probability would go down, but in fact it went up. And it's Bayes' theorem which enabled us to calculate this and get a more informed estimate of the probabilities of these diseases.
So what has happened so far? We've seen the original probability of the three diseases, and we've seen how information about a symptom can change those probabilities for a particular patient. And we've done this using the concept of conditional probability and the technique of Bayes' theorem. But of course, looking at a single symptom is just the first stage of the diagnosis. We need to consider several symptoms and see how, together, they affect the probabilities of the diseases. Now, in certain circumstances, you can use Bayes' theorem for that too.
We'll show two symptoms on the Venn diagram. The symptom S1 is the one we had before, daily pain. Here's a new symptom, S2. We now want our conditioning event to represent the patient suffering from both S1 and S2. And we'll do that by applying Bayes' theorem to each symptom in turn. Here's the first symptom, S1. Now we'll regard the people with symptom S1 as constituting the whole event space. And we'll apply Bayes' theorem again using S2 for our new conditioning event. We can do that where S2 refers to people who are under 60 years old. That doesn't sound like a symptom, but it is information about the person with the illness. The chances are that a person with gastric cancer is likely to be older than a person with either kind of ulcer. So I'll feed into the computer the three conditional probabilities. First, the one that refers to duodenal ulcer, 0.911. Then the one referring to gastric ulcer, 0.769. And finally, gastric cancer, 0.350. Now, those are the new conditional probabilities. Let's look at them on our diagram. Remember, that's where we left our diagram with one symptom, and now we'll put in the second symptom. As we expected, gastric cancer is now rather less likely. And it's beginning to look like duodenal ulcer, or possibly gastric ulcer. In the project at Glasgow, the patient answers a series of questions. Depending on her answer, the probabilities of the diseases change. Obviously, the real-life problem is vastly more complicated, with lots of interrelated symptoms and the chance of more than one ailment. The calculations can't use Bayes' theorem in the straightforward way we've described. But they do use the idea of updating conditional probabilities to provide the GP in the health centre with the specialist's expertise.